Good morning. Good morning, all of you. So, please let me know in the beginning, is my voice audible? Is my voice audible to you all? I hope there is no problem with the voice. All right, all right. So today it is time for us to go forward in our lesson where we are talking about diffraction of light, right? So we have started with diffraction of light at a single slit. Then we have moved on to doing the completion of double slit as well. And moving forward, from today, we are going to talk about Fraunhofer diffraction at n number of slits. Alright, so we are as if generalizing the entire diffraction chapter into n number of slits where n can be any value, it can be greater than 1 with any given value as per our choice. But sometimes we'll see that this diffraction occurring at n slits is also considered to be diffraction occurring at the grating, using a grating. Now, there is a very small difference or point which I want you all to understand, that when we in general talk about diffraction from n slits, this n can be 3, it can be 4, it can be 5. Very small numbers as well. However, whenever we are actually talking about a grating has this n to be very, very large. Number of slits are very large in terms of thousands. Alright, so what is exactly a grating and what are its specialities or how we can use this n slit diffraction results, we will be talking in a upcoming class. However, today what we are going to see is how diffraction occurs, or what are the different points that we have to discuss when the number of slits is not 1 or 2 but more than that, where n can be any given number of our choice. Alright, so this is what we are going to study today. Now, if you can see the figure that I have already drawn over here, what is the difference between the single slit and the double slit pattern over here, the diagram? The only difference is here I have drawn a number of slits. See what I have done. In the beginning, over here I have drawn a few number of slits. As you can see, I have called, say, the slit number 1, 2, 3, 4. And I have drawn a discontinuation, and the last one which I am showing you over here is as if the nth slit. This n can be any number, say 10 or 20 or 500. Okay. So we are having a multiple slits. We can also call this as diffraction occurring at multiple slits. So what will happen? A part of the rays from all these slits will be moving forward without bending, without showing any theta inclination, and they will be focusing on the point P0 on the screen. This is just common like that of the double slit as well. However, when individually all the rays will be, say, diffracting by an angle theta, where will they be focusing on the screen? They will be focusing on any random point P1. Alright, and depending on the values of theta, they will be giving us, as we have already seen, we can be getting maximas, minimas, and so on. Alright, now the basic difference which I want you all to understand before we begin is that we are now not dealing with one slit or two slits, we are dealing with multiple slits. Alright, so what are the points that we are going to discuss or finish in today's class? Just like all the earlier classes or all the earlier topics with single slit or double slit, we will be following the same points. As first, we will begin with path difference. From path difference, we will be calculating the phase difference, which will help us to find out the resultant amplitude. And from there, obviously, we will be calculating the resultant intensity on the screen. Okay. And in today's lecture, in today's class, I will be moving forward with the fifth point, where I will be talking to you about the conditions of central maxima. We will talk about the condition of central maxima, and with this central maxima, I will be showing you that how much can be the intensity of light at central maxima. So these are the 5 points that we are going to discuss today and do the derivation of. Okay. So with these points in mind, let us start our discussion or calculation. So first thing first, we will first go and find out the path difference. Now the question might be coming to your mind that path difference between whom? Whose path difference are we calculating? Now see, when we were, suppose there are only slit number 1 and slit number 2. What would you do? You would think that what is happening over here? Individually, slit number 1 and slit number 2 are causing diffraction. In the same manner, when we are having n number of slits also, all these individual slits are causing diffraction to occur within themselves. And what will happen? Individually, we have already calculated that what will be the resultant amplitude and resultant intensity caused due to single slit. That remains same over here as well. However, what is now extra? The extra point in this scenario is the interference occurring between slit number 1, 2, 3, 4 as well as going forward till the slit number n. So in double slit, the interaction or the interference was occurring between the light sources from slit number 1 and slit number 2. Here it is occurring from all the provided slits from 1 to 2, 3, 4 till n. So in this case, what are we going to do? First, let us find out the path difference between source number 1 and source number 2. What do I mean by source number 1 and source number 2? Source number 1 means the wave which is passing through the slit number 1. Source number 2 is any particular wave which is passing through slit number 2 like this. So what will be the phase difference between them? As usual that we have been doing till now, I can draw a perpendicular, and if this angle of diffraction was theta, this angle can also be called as theta. We have already discussed this once and twice in case of single and double slit. So you all will readily agree with me when I write that this path difference between, say, source number 1, path difference between source number 1 and source number 2 can be written as A plus B sine of theta. Why A plus B? Because individually the slit width is A and the slit separation is B. Agree? Now if I ask you, what is the path difference between source number 2 and 3? What is the path difference between 3 and 4? You all can draw similar diagrams, similar perpendicular to individually successive all the sources, and you will see that path difference between 2 and 3 is also the same. Path difference between 3 and 4 is also the same. Isn't it? So individually, as we are moving forward with our sources or the slits, the path difference between individual or successive sources remains the same, which has the value of A plus B sine theta. Fine? So if this is our path difference between the successive sources, what will be their phase difference? What will be their phase difference? Their phase difference now can be written as, 2 pi by lambda into the path difference, which is A plus B sine theta. Alright, so as if now what is happening, we are going to calculate the effect of superposition of n number of sources. And what is the relation between these n number of sources? Successive sources is having a path difference, or rather phase difference of 2 pi by lambda A plus B sine theta. The phase difference between 1 and 2 is this, 2 and 3 is this, 3 and 4 is this, and n minus 1 to n is also this. Correct? Yes, very good, Rupa. So we have understood this part. Alright, so now if I want to ask you, or if I want to remind you that at this juncture, what are the information that we are having? Let me remind you that due to the diffraction occurring at, say, slit number 1, due to the diffraction that has occurred only due to slit number 1, what is the resulting amplitude that it is moving forward with? What is the resultant amplitude? Remember, it was n into A sine alpha by alpha. Right? So, in case of, say, NA, if I am using, say, A0, then it is individual. All these sources. Source number 1 is having the amplitude. This wave is having the amplitude A0 sin alpha by alpha, which we can get from the result or the calculation of single slit. So individually, now that I am discussing about slit number 2, 3, 4 and n, all these individual sources or all these individual waves are coming with the same amplitude A0 sin alpha by alpha. The reason behind this is we have considered that individually all these slits have the same slit width as well as the same slit separation. As a result, individually all of them are having A0 sin alpha by alpha as the resultant amplitude, right? So with this thing, now what is the extra information that we have calculated? The extra information that we have calculated is along with this amplitude of each of the waves, now we also know that from slit, this source number 1 to source number 2, their phase difference is 2 pi by lambda a plus b sin theta. Again from 2 to 3 it is the same. So as if we are now going to find out the resultant. Let me just rub this part. As if we are now going to find out the effect on the screen of what? Of say n number of vectors. Say one of the vector, if I call this as my resultant wave of slit number 1 and this as the resultant of slit number 2, the same as we have done for double slit. What is the phase difference between them? Their phase difference between them is 2 pi by lambda a plus b sin theta. Let me call this angle as say angle phi. So the phase difference is phi. This is the phase difference between 1 and 2. Now suppose in this case, since we are working with n number of slits, there is another vector which is the source number 3. But then what is the angle between 2 and 3? Or rather the phase difference between 2 and 3? Once again phi. Now there is another say source number 4. And again, what is the angle or phase difference between 3 and 4? The same angle phi. So as if now we are adding up or we are trying to calculate the result of n such superpositions, and with the information that individually all of these are having the phase difference between the successive sources as phi, where phi is 2 pi by lambda a plus b sin theta. Alright, so like this, suppose I was having another source, say n number. So what will be my resultant? This will be my resultant. Right? And this resultant, say, what shall I call it? Because we are doing it for n number of slits, say, let us call it as the resultant of n slits. Let me call it as RNS. So this is what we have to now calculate. Right? Now, reminding all of you, I do not need this diagram anymore. So let me rub this away. So let me remind all of you that when in case of calculating or studying single slit, I had told you that the addition, when we are trying to add these kind of vectors or harmonic functions, the resultant comes out to be, the resultant can be given by a particular formula, and that same formula can be used in this discussion as well. However, I am not going into the individual derivation of adding up all these things, which is not actually required for our syllabus, but you can always do it. Remember in double slit, we had done it for the 2. So like this, we can do it for 3 and 4 and n as well. However, today let us move forward with the final result. And what is that result? The resultant amplitude due to n number of slits is given by the resultant due to single slit, the amplitude which we have received due to single slit, which I may call as we were calling it as, remember, A0, or we were calling it as n into A. We were calling it as n into A, right? So let me just not move to that. Let me just write it as the resultant amplitude due to single slit. And now what will come in? The contribution from all the phases. And that phase is given by sine n phi by 2 divided by sine phi by 2. Remember, the same thing we had used, this result we had used in case of our single slit as well. Alright, so this is as if when lot number of vectors are added with individual phase differences in between them, the resultant amplitude is formed by this particular formula. However, now if I want to write down what is RSS and what is phi, I can put down those individual values over there and I can get the final expression. So reminding all of you, how much was this single slit amplitude? Reminding all of you, it was n into A sine alpha by alpha for a single slit. And in case I don't want to write this, I may write it as say amplitude 0 sine alpha by alpha. This is what my RS, the resultant due to single slit is. Okay. So with this in mind, now I'm going to put in the value of sine n phi by 2. What is phi? Phi is 2 pi by lambda a plus b sine theta. So when I'm dividing it by phi by 2, what am I left with? I am left with sine n a plus b sine theta, rather I should be writing it as pi by lambda, and divided by sine phi by 2, so that will be pi by lambda a plus b sine theta. Alright, I hope all of you are with me while I am writing this. However, if I ask you, what did we call this particular quantity, pi by lambda a plus b sine theta, in the last class where we were discussing the double slit? Remember, we had called this very angle as the angle beta, isn't it? So what I am getting over here, if I call this pi by lambda a plus b sine theta as the angle beta, what am I left with? I am actually left with sine n beta by sine theta. Alright, and once again I will remind you that whenever you are writing this particular expression in your copies, do not forget to write that alpha is equal to pi by lambda a sine theta and beta is equal to pi by lambda a plus b sine theta. And dear students, this is exactly the resultant amplitude caused due to the diffraction of sources passing through n number of slits. Alright, so this particular expression that you can see over here is our desired resultant. Alright, so this is where we are now standing. So from here, resultant amplitude as usual is our point number 3. So when we move forward to the number 4 point, which is actually the resultant intensity, what are we supposed to do? We all know that intensity due to n number of slits is nothing but the square of the resultant due to n number of slits. All we can do is, we can write down this intensity due to n number of slits very easily as sine square alpha by alpha square sine square alpha by. This is the expression for intensity due to n number of slits. Now, dear students, please see one thing. If I now tell you that suppose there is a student who has only remembered the intensity formula for n slits. He has forgotten the exact formula for single slit, for double slit. Then it is not a problem that if he has forgotten them. If any student knows this particular formula, by putting in the various values of n over here, he can always find out the resultant intensity. How? I will tell you. Suppose I want to know, I have forgotten what is the resultant intensity due to single slit. In case of single slit, what is n? N is 1, right? So what will be this value? Sine beta by beta or sine square beta by sine square beta. So this part will go to 1 and all we will be left with is a0 square sine square alpha by alpha square. And see, this is nothing but the intensity for single slit, right? Now suppose I want to ask you, or that person wants to find out what will be the intensity for double slit. All that person has to do is to put in n is equal to 2. Right. So when I put, say, then I will be having the quantity sine beta by this, and this n in that case is 2 beta, sine 2 beta, correct? And what is sine 2 beta? Sine 2 beta is 2 sine beta cos beta. Sine 2 beta is 2 sine beta cos beta. And this, when I'm dividing by sine beta, what am I left with? Sine beta is getting cancelled and I am left with 2 cos beta. And when I'm squaring this, because I have the quantity as a square over here, what am I having? 4 cos square beta. So instead of this, if I write as 4 cos square beta, remember what is that? Again, that is giving us the intensity for double slit, isn't it? So this can be considered as the general formula. So it will suffice that any student will remember only this formula and can then find it out to use any n of his or her choice. Alright, so this is a very general formula for calculating the intensity due to n number of slits, where n can be anything from 1 to say a very large number. Alright, so this was our point number 4, which was intensity. In today's class, the next point that I will be discussing is to calculate the condition for central maximum. Alright, so let us move forward. I'll keep this over here and the rest of the things we can just rub off. So now what are we calculating? We are calculating the condition for central maximum. Now, students, sometimes you will also see that in your books or question paper, instead of central maxima, the term principal maxima might also be used. So please do not get confused that they are asking something else. The terms are the same. Central maxima or principal maxima actually denote the same. However, now that we have the expression for intensity over here and we have to calculate the condition of central maxima, I want all of you to just remember the diagram that we drew. And if I ask you, if you do not even know this particular formula, if I ask you where is the central maxima formed, you all will readily say that central maxima is formed where the rays have not deflected by any angle and they have moved in a straight line and they have focused on the point P0. Remember? And what is that particular condition that you all will agree with me for getting the value central maxima or the condition for central maxima? Where theta is 0, isn't it? Where the rays are not bending at all. So from here actually, when I get back to the known equation of intensity over here, actually the particular term which causes this is this sine square beta term. Alright, so actually as a condition, if somebody is asking you, you should be writing sine beta is equal to 0. Now, please see over here that in this case, when we were doing sine square alpha by alpha, the value of alpha could not be taken to be individually 0 because that would blow up this entire thing. However, now when we have come down to n number of slits, the expression is no longer sine square alpha by alpha. It is sine square n beta by sine beta. The sine function is remaining and hence the conditions are changing. Alright, so there is no contribution from cos over here. Everything is coming from sines. Okay, so as I was telling you, sine beta, this factor should go to 0 because this will actually eventually lead us to theta is equal to 0. Alright, so and if I start from here, what are the values of beta which will give us this? They will be sine of plus minus m pi. I am not using the term small n so that we are not confusing between the earlier numbers. Alright, so sine m pi. So what is this beta then? This beta can be written as plus minus m pi. And reminding all of you that what is this beta himself? This beta is nothing but pi by lambda A plus B sin theta. I should be writing it. No? Pi by lambda A plus B sin theta is equal to plus minus m pi. So what am I getting? This pi and this pi is getting cancelled, and I am getting the equation or the condition for central maximum as a plus b sin theta is equal to plus minus m lambda. This is the condition for central maximum. However, students, please see the difference over here from single slit, that in this scenario, what are the values of m? This m can be 0 and 1 and 2 and 3 and so on. Are you following me? In this case, we do not have the condition that m cannot go to 0. Alright, m itself also can go to 0 in this particular n-slit case. Okay, so this is where we are now standing. So, as I was telling you in the beginning, that along with getting the condition for n-slits, I am also going to tell you about the intensity of the central maximum. Please see, what am I trying to tell you now? We need to calculate the value of maximum intensity, which is the intensity of light at the central maximum. When these theta values are taking, when a plus b sin theta is plus minus m lambda, what will be the intensity of light, which we can calculate from here. But children, here the determining factor is the sin beta, sin n beta by beta, correct? Let me just show you this part. So this is the determining factor over here. But when I am going to put, so basically we are dealing with the factor sin n beta by n beta. Square can also always be done later on. Whenever this beta is going to take the value of 0 or a plus b sin theta is going to take the value of m lambda, what will be the value of this particular term? The numerator is also 0. The denominator is also equal to 0, isn't it? So then what will be the resultant? This is as if giving us this is a indeterminate value. So we are not able to calculate the value of sin n beta by beta. So does that mean that we will not be able to calculate the intensity of light? Will that be so large that we cannot measure it? The answer is no. What has to be done here, what has to be remembered and used in this scenario is once again our limits. Reminding all of you, we will be using the L'Hospital's rule. Alright. I know I am distorting the French name very much. He is not to be called as hospital as they call in French. But for us Indians, let him be the L'Hospital. And let us now use L'Hospital's rule into this particular scenario and try to calculate the intensity of light caused at the principal maximum. Alright. So what will I do? Reminding all of you that in this scenario, the L'Hospital rule that we can use shows or can be used over here as limit beta tending to plus minus say n by. What can we do? We can do the differentiation. dd beta of sin n beta by dd beta of sin beta. Within the limit, the value of beta tending to plus minus m pi. So when I do this, what will I get? Differentiation of sin n beta will give me n cos n beta. Oh, obviously I have to write down the limits. I cannot forget that limit beta tending to plus minus m pi. So dd beta of sin n beta gives me n cos n beta, and dd beta of sin beta obviously will be cos beta. So this is where now we are standing using our L'Hospital's rule. And now when I put the value of beta as plus minus n pi, what will I get? Plus minus n pi, plus minus n pi. Dear students, please tell me, what will this be? Cos of any multiple of plus minus n pi is 1. In this case also it is 1. So what am I getting from here? The value of sine n beta by sine beta in the limit beta very close to plus minus n pi is actually the value n. And in our intensity, remember we had this particular sine n beta by sine beta as a square. We had sine square n beta and sine square beta. Then when I'm going to put this value of n over there in our formula, what will be the intensity received? The intensity or the maximum intensity, at central maxima due to n number of slits will be I0, or as we were writing it as, I guess we were writing it as A0 square sine square alpha by alpha square to n square. So please note this value over here, students, that larger this number n, larger will be the value of intensity. Remember when we were just discussing about single slit and double slit, by changing from a number of slit 1 to number of slit 2, the intensity had increased by 4 times. Remember we had a 4 in front. And here as we can see over here, this is actually coming it out as n to the power 2. So higher the number of slits we are considering, or it's there in the case, higher will be the maximum or the intensity received at the screen. Alright, so this is the last point which I want to discuss in this particular class. So before I end today's class, let me just take a recap or summarize the entire class that we have discussed today. So we have started with the figure of n number of slits. You all should be able to draw the figure if required. Then what did we do? We found out the path difference between the individual sources. And whom did we call as sources? The ray which was due to single slit, then due to slit number 2, then due to the slit number 3 till the slit number n. So we first found out the path difference between them. After calculating the path difference, we just moved forward to the phase difference. From calculating the phase difference between these n number of sources, we then found out the resultant amplitude of these individual sources when they have superposed. And from the resultant amplitude, we received the formula for resultant intensity, which we wrote as intensity due to single slits. We found out as sine square n beta by sine square beta. So these are this particular formula I also told you that can be remembered for utilizing in any number of them, one or two or any large number you want. So this was the intensity, and finally in today's class the last point that we discussed was the condition for central maxima, which we have written down already as a plus b sine theta is equal to plus minus m lambda. Remember all of you, in this case it will not be sufficient if you just write like this. We should always be mentioning the fact that m is equal to 0, 1, 2 and alright. So that is all what we had to study in this class. Further, the conditions of getting secondary maxima, the condition for minima and their individual intensities caused by them, we will be discussing in our upcoming classes, and then we will move forward to utilizing these results for the grading. We will also talk about grading, and that is all we will be requiring to study in our diffraction chapter. Alright, so that is all for today. I hope you all have understood. Okay, so bye bye all of you. Take care.